Hi everyone. Today let me give you the third lecture on energy method. Before we begin, let me give you the review of a previous lecture. In previous lecture, we discussed about work energy method. First, we discussed about work energy method for single load, and then we discussed about work energy method for a multiple load. So the example we considered was a bending of a simple cantilever beam on the point force P, and especially we found that we can even consider the case with small aspect ratio or error over D is less than 10. So the first approach we have done was we considered the energy conservation method work done, which is the due to the point force at the end, which can be written as 1/2 p times ym because the force increases linearly from 0 to maximum. So this work should be conserved and converted as the strain energy of the beam, and by considering the strain energy due to normal and shear stress, we by equating half p ym equals to bu, we obtain y as a function of p and other material properties and geometric constants. In addition to this work method, we also considered the derivative of strain energy method. After obtaining strain energy in terms of p, the point of force, if you perform partial u partial p, it turns out to be y, or displacement at that point. Okay, so I told you that we can apply the method for point force, we can apply the method for point moment, we can also apply the method for the point torque. Okay, so or point torsion. So whatever point force or point torque you are considering, yeah, you can use a similar method. Yeah, the only difference is you can obtain either the length dimension, which is displacement, or dimensionless numbers such as bending angle or the twist angle. Okay, in addition to that, we considered a the structure under like a given axial loading, no, not axial loading, given point loading. So here the way we approach this problem is we first consider internal force FBC, internal force FAB, and we write down FBC in terms of P, we write down FAB in terms of P. Because we can write down U in terms of FBC and FBA, with doing this, we can obtain U as a function of P. After obtaining U as a function of P, after performing partial U partial P, we obtained that 0.728 PL over AE becomes the answer for this problem. So the key to this problem is, write down all the unknown reactions in terms of point force P and obtain the strain energy in terms of P. Then everything, resolves quite easily. Partial U partial P is quite easy to perform, and you obtain the deflection at point P along the vertical direction. Now, after we discussed about work energy method for single point load, we discussed like a double point load problem, where we have like a two locations on the point force 1 and point force 2. After all of these discussions considering P1 first and P2 later, or P2 first and P1 later, what we have found is that due to the superposition principle, your final answer should be equal to each other, and because of the equality, we found that alpha 1 2 and alpha 2 1 must be equal to each other, and it is so-called Maxwell's reciprocal theorem. And because of this equality, we were able to show that y1, the deflection at point 1, and y2, deflection at point 2, can be written as partial u partial p1 partial u partial p2 when u is written in terms of p1 and p2. Okay, and after showing that this is true for 2-point loads, we asked this question: what about more than 2 loads? What about there exists 3 loads and 4 loads? What about if there is no point load? Like, for example, we can only have distributed loading without any point force, without any point moment, without any point torsion. Then can you use this strain energy method and partial U partial P method? Okay, so regarding these questions, we're gonna answer today's class by considering Castigliano's theorem and statically indeterminate problems. Okay.